This talk is probably aimed a little more in the entertainment side than the education side, in that I'm not sure you're going to be able to use a lot of it, but it doesn't matter, we're going to go with it. As Niall said, I'm a software engineering manager these days, but from the talks earlier on in the week, I think I'm in platform engineering, which is basically SRE with a different hat, like flat cap. I don't know. I'm doing platform engineering, but I've done a lot of things over the years. So I was trying to, where have it been SRE? Most of you are probably product SRE in that you're concerned with external customers of your employer or your organization. You care about latency, reliability, capacity. Most product-based SREs care about latency in the human reaction bounds, maybe 100 to 800 millisecond type thing. Product SREs will get direction from a VP somewhere that has a giant lever that goes from reliability to velocity, and the SRE teams tries to make both better at the same time, but of course they're paying attention to where that lever is. Happy product SREs should be able to ship multiple times a day. I remember seeing slides where this was insane 15 or 20 years ago, but now it's really easy. Everyone can ship multiple times a day. It's great. But a good number of the audience are going to be infrastructure SREs. And these are different, right? These are the doozers who ensure product teams can spend more time caring about customers and less time about the tools and the building blocks that their products are built on. Infrastructure SRE tend to concentrate on important abstractions like networking, compute, storage, distributed system components like lock servers, service discovery. Infrastructure SREs, they make these abstractions seem easy to use and rock solid and reliable for product teams. In a previous life, looking after a storage system, we had to give people the bad news. There was an explosion in the data center, a load of whatever gas was released, static cables were thrown 20 meters, hard drives were blown out of machines, and we said, sorry, all the data's gone. And they were like, what do you mean all the data's gone? It's a reliable file system. And it's like, well, yes, until you physically remove parts of the servers while the service is going and scatter them across the data center floor, and then it's no longer, it's more of a selection of X components. Sorry, you're going to have to restore from backups. And they were devastated because they thought we did all the backups and we did all of the data and we looked after the storage. It's like, nope, you give us blocks, we give you blocks back most of the time. The unofficial motto, of course, for that SRE team was, you can always make more data, which is true. And they did. It was fine. Yeah. So infra SREs tend to care about, similar things, but not quite the same as product. Efficiency, resilience, stable APIs are a big deal in the infrastructure world. Latency can vary from microseconds, maybe you're running a Memcache server, to hours. Maybe you're doing some kind of workflows or machine learning pipelines or something like this. The reliability versus velocity balance tends to skew a lot closer to reliability and less toward velocity. Infrastructure SREs are going to be happy if they can ship weekly. You're not going to ship new kernels multiple times a day. It just makes people sad. So let's think about it. How lower in the stack can you go? Right? The lower you go, SREs get harder to find. What's below infrastructure? Maybe security? The people who care about like provisioning bootguard, or the people trying to spot interesting system call patterns or something like this. Maybe asset management. It's a bit weird. Some kernel companies had kernel SRE. We heard from one of them recently where they're managing the kernel and deployments. But it's pretty niche, it's not common. So I'm going to suggest that SRE probably has some more growing to do below infrastructure. I'm going to start with an interesting one. The machines you run, they run Linux most often. What if I told you, though, that's not the only software they run? And the majority of you probably have no idea what that code is, where it lives, how it fails, or how to debug it when it goes weird. There was a fantastic talk, you can grab it from the slides later on, but Timothy Roscoe did a talk for OSDI, I think it was, last year, on modern hardware on Linux and how Linux people need to know more about the hardware than they have been used to traditionally. A modern server basically is composed of hundreds of microcontrollers and many full-on processors. Only the tiny minority of those are running Linux or an operating system or anything that you have access to. And many SRE philosophers, is that a real job? It kind of feels like it's a real job. It's not like a pay, well, maybe it's a paying job. Yeah, well, no, yeah. We don't have pub philosophers as much anymore. So many SRE philosophers will say you can't really SRE something that you don't have source code to, right? Because you can't see into it, you can't really reason about it, you can only guess about it. You might struggle to effect change. What's the point of being an SRE for something that you can't improve? And modern hardware has a lot of software that you do not have any ability to influence. So here is a block diagram of a NVIDIA Jetson. It's about the size of a fist. I didn't mean that to sound threatening, but it's about the size of a fist. And it has software all over the place that you have no idea what it does. PCI Express is ludicrously complicated these days. It's not just about moving bits around. It can do all sorts of great error control, multiple buses, training. It's really, really complicated. GPUs, obviously, you probably download, if you have a video card at home, you occasionally download another 200 megs of drivers. There's a lot of code in that. Memory controllers are ridiculously complex these days. They do serious voodoo magic on machine startup, trying to train RAM and work out how the RAM is better. In fact, a lot of people who are experts in memory say there's a lot more innovation and super secret sauce in the software on the memory controller these days than there is on the hardware that the RAM is made of, because if you just don't have good software, your RAM might work half the speed and no one will buy it. CPUs can have switch fabric. That's going to be really complicated. There's a few, they call them bridge ICs there. I am not going to discuss them without a pint in my hand. Not happening. Yeah, security chips are a complete nightmare. I've never met a security chip that worked properly. Like they have a specification, they just don't meet it, and they assume it's too complicated for anyone to try and understand if it does its job, so they move on. So the network chip actually probably has more lines of code than a rack of servers did 20 years ago. Modern network chips, they might do remote DNA, or DMA. Remote DNA is probably very different. Remote DMA, they'll give full memory access to other machines on the network, to your machine. Your operating system won't know anything about it. It just magically things change. It can do the equivalent of eBPF and all inbound and outbound network traffic. And again, your box can no longer trust or understand what's going on the network in reality. It's, yeah, and all of this software can go wrong. If I was to guess how many lines of code, I would be saying like somewhere between 30 and 50 million lines of code that you can't audit, you can't see, and it influences your business every day. So let's take a few little examples. I have to start with system management mode because it's insane how much pain and suffering something so simple has inflicted. It was invented in the late 90s when laptops were invented that could close. So imagine you're running Windows and you close your laptop lid. Windows would get a signal saying you should, shut down, go into power saving mode. And if Windows didn't and you put your laptop in your bag might catch fire. So they said, how about we don't trust this to Windows? What's the simplest solution for this? We'll just have a little interrupt and have a new mode on the CPU, the system management mode, that is underneath the operating system, completely invisible to it, and it takes complete control of the machine. And if that's really simple and well written, it'll definitely always power the machine off. So no one's ever had a laptop that they closed it, put it into their bag, and then half an hour later, the bag was really warm, right? It breaks occasionally. But here's the worst thing. That has now been repurposed for anything that makes the firmware writers' lives easy. They'll just throw it into this system management mode. So system management mode, you can install multiple programs. They have to do cooperative multitasking. I'm sure that's going to go fine. And all of these programs, they can do whatever they want on the operating system. They can stop the machine, stop all the cores, poke away at memory, change things, change hardware settings, and then wake the machine up. And the operating system just sees its timestamp has changed. And that's the only notification that it got, that the system management mode did something. I had a discussion at a conference a while ago with a guy from the NSA. And his job was to write software that could look for system management node handlers that shouldn't be there because he didn't like it. And I said, oh, cool. Have you written your own? He said, oh, yeah, loads of them. And, oh, what do they do? Well, I can't tell you. And like that, yeah, he could put a system management mode handler in any machine and you couldn't tell about it. A great security exploit, actually, would be to, once you have root access on a machine, you can probably get a system management mode handler installed into the firmware, and then every time that machine boots up, it'll run that. Maybe it's a keylogger that wakes up, stops all the CPUs in the OS, sends out data over Wi-Fi or whatever, and then wakes the operating system back up. Absolutely possible. So in general, you probably don't want this mode, but in general, every piece of hardware, Intel hardware or x86 hardware is going to have it. Yeah, scary stuff. So the first time I learned about this, we were qualifying a new platform. I was tangentially related, but the developers who cared about latency were tearing their hair out. They spent about 6 or 8 months trying to work out where were random 100 millisecond latency blips coming from. Just out of nowhere, RPCs accepting, it just went off the scales. They couldn't find out. After 8 months, they found the system management node handler for logging ECC errors. Now, not fixing ECC errors, just logging the errors, was written in 16-bit code. So their brand new 64-bit servers were stopping all the cores on the server, hopping back to 32-bit mode, hopping back to 16-bit mode, writing a setting to NVRAM, and then doing the whole thing back. But it took 100 milliseconds because no one in their right mind was optimizing a modern server for 16-bit mode anymore. So yeah, you can assume if you don't have access to source code for your firmware, there's a decent chance you could have some 16-bit code in there. Yeah, it's a sewer. So I came across another platform where firmware updates took 35 minutes to run. That's a kind of a problem because if you're trying to upgrade firmware and you get a random reboot, on scale, you're going to have these problems. The machine is now bricked. Also, when you're doing development, it's a real pain or testing firmware, it's a real pain to wait 35 minutes. We looked into it. Turns out the microcontroller that was writing the firmware to the device, to the flash, it was doing the writes in 144 byte blocks from the BMC. And the BMC, every time it was passing this 144-byte message, it was turning up a Unix domain sausage. A Unix domain socket right in the 144 bytes, tearing it all down. So the bus electrically should have been able to write the firmware in 30 seconds, but it was taking 35 minutes. No self-respecting engineer would write code that bad if they thought somebody else was going to read it. And that's how firmware is written. They're assuming no one's ever going to read it, so it's fine. That got all the way through to production because no one in their right mind thought to test how long does firmware take to flash. Another one had an interesting security feature where if any firmware was changed, it would check all the firmware's signatures just in case of a compromise. Very, very cool. It means no firmware in the whole system could be compromised. Everything had to be signed. Very, very cool. So during early testing, made a change, rebooted, and the machine took 20 minutes to reboot. I was like, what the hell happened? Well, the maker used the slowest microcontroller that they could find that would meet the letter of the spec to sum all of the flash. But like on modern machines, that could be reading 200-300 megs, and it's trying this on a little Arduino-type microcontroller, or probably an tiny, something really ridiculous, because they didn't want to go for the 40-cent chip. They went with the 15-cent chip on a $1,000 motherboard. Why not? Anyone here run a service that might be upset if machines took 20 minutes to reboot every so often? Yeah, it wasn't good. It wasn't good. Hardware requirements can be like asking a genie for a wish when they actively try and make you as miserable as possible while making the letter of the wish. Another thing you'll hear a lot is that, customers don't mind. I was confused. Another platform took ages to boot. Someone with more firmware expertise than me, they were digging into it. They had a look at why it was taking a long time. And one thing they noticed was it had 3 copies of VGA drivers that were all fighting over each other to initialize. It was a server. It didn't even have VGA. So pull those out, boom, knocked 40 seconds off the boot time. But it was still kind of slow. And so I had a look, and it was printing a lot to the serial console. And I was like, I wonder how much. 8 megs. 8 megs at 57,600 bits per minute. Oh my God, that's 90 seconds alone just outputting the text. So this bugged me for ages. I mentioned it to somebody at a conference, and they went, oh, that chip. Oh yeah, there's a bug in the hardware. So if there's 4 cores or fewer, it just boots up fine. But once you go more than 4 cores, the firmware has a race condition and locks on boot. But if you enable debugging, the printf statements make it work. And I was like, but this is production. Like, we've been using this for a year or two. And it was like, yeah, we have source code access, so we just got the source code, fixed it ourselves, and gave the patch to the silicon vendor. Ask them. So I asked the silicon vendor. They said, but enabling debugging makes the problem go away. Why are you talking to us? Well, we don't want debugging running in production. Well, no customers have complained to us about it. It's like, well, we are. I know one other. And they're like, oh, whatever. And everyone, of course, would have liked their machine to boost 90 seconds faster. Eventually, they said, look, it's an older system. We don't plan any new firmware releases. The firmware has no serious bugs. It's like, it's not really serious, is it? And it's like, no, it's just a pain. It's just bad workmanship. So I gave up. An engineer in the know later on explained to me that when that firmware was written, the team was then broken up and reassigned to other projects. Probably all the test hardware was broken up and assigned to other projects. So if we wanted to get a new firmware release done, they'd have to reassemble a team, have them skill up on the development process, run through all the testing, find the hardware to test it, and they're like, yeah, you'd really, really want to make them want to do that. And I was like, okay. Also, upstreaming is really risky, right? Imagine you buy a server from a company, spot a firmware bug, maybe DHCP code or something like this, and you go, I wonder, is that in the original DHCP code for UEFI? So you can download the reference implementation, you can go through it and you go, oh, I found the bug, that's amazing. It's probably in every firmware out there. So you contact your vendors and start saying, hey, we found this bug, and they go, yeah, but do you really want to fix it? And eventually you convince them, yes, it's a problem for us, they fix it. And then you buy another server from the next month and it doesn't have the fix. And it's like, what? It is so risky. They don't want to upstream anything, right? Nobody upstreams fixes. Because imagine this bug that nobody noticed for 10 years, but it was annoying us, and they fix it, and then suddenly, I don't know, a 300,000 person company uses it for deploying machines, and you've broken their use case. Well, when helping people and I suppose fixing bugs is so risky, and it's all downside and no upside, altruism just goes right out through the window. Now, common factor in these is any of the code under the OS, we just can't see it, we can't change it, we can't review it, and it limits the actions that operations can take after the platforms are shipped. And let's see some other kind of suboptimal, or sort of some interesting cultural aspects of the hardware industry that have resulted in suboptimal firmware decisions. So, yeah, web devs, they ship hourly. A new server platform is considerably longer. So imagine something that's shipped in 2022. Its requirements were defined 5 years ago. It was designed 4 years ago. The chips were sampled in 2020. It was a terrible year, I don't know if you remember. Then those chips were tested in 2021. We probably had supply shortages, things were delayed. It was eventually shipped. And then SREs, maybe late 2022, suddenly found bugs, and everything was terrible. Well, it's going to be a lot longer until the new chips can be fixed, shipped, and the original ones thrown out. They're not good. Also, yeah, do you remember back in the 80s, maybe early 90s, there was a divide bug in a certain chip? Anyone remember? Right. Like, that was 30 years ago. Like, get over it, right? I'm glad I'm not married to you. At the same time, there was bugs in like Windows and DOS, and they caused machines to crash, and nobody remembers them. But we still not remember the name of the bug 30 years later. So yeah, I'd say, yeah, people just have long memories for this, and this makes hardware people very, very conservative. And software people, they can just push a fix, it's good. But if you make a hardware bug, you go, oh, do we really want to fix it in the hardware? Just do it in microcode. Oh, do we really want to do it in microcode? Maybe we'll fix it in firmware. Oh, do we really want to fix it in firmware? Maybe the kernel can work around it. Do we really want to fix it in the kernel? SRE will find a workaround in the application. It'll be fine. And by the time SRE realize they can't do a workaround, someone will go, look, it's 6 months until a new platform will be out, and maybe it'll be fixed there. Why bother fixing it at all? It's great. Yeah, so different people have different things, and the schedule is king. Like a team of project managers who coordinate engineering, sales, testing, finance, marketing, logistics, all of the parts from dozens of companies to arrive in the factory in the same week so that you start making hardware. Like, you can't reschedule that. A week of a delay could cost millions, could destroy the reputation of a company. It's just not done. So, hardware engineer will push back and go, look, can we get a workaround? It's going to take us 6 months to fix this anyway. And then once you have the workaround, well, why do we bother fixing it anyway? Because you've got the workaround. And so this leads to a really horrible, vicious circle. Ops basically go, well, what's the point in complaining to the hardware people if they don't fix it anyway? We just won't bother logging bugs. So what our hardware goes, our platforms are awesome. Nobody logs bugs. Like, everything is amazing, promotions all around. What would the SRE philosophers say about this, right? They'd probably say you're in a toxic relationship with your development team. Ops can't just walk away from low-level infra, even if we feel ignored. We're just going to have to engage. We're going to have to log those complaints anyway. Maybe it doesn't result in anything happening in the next year or two, but it'll hopefully get better eventually. What can SREs do? Well, we can help with the DC techs, with automation, help them with qualification. Infra SRE need to be told early on, like what the nasty parts of a hardware platform are going to be. SRE are great actually at working on things like requirements and adding new things that should be caught in future. They also need to get involved much, much earlier, right? They need to find bugs much earlier. There's a chance you can get it fixed in firmware if you catch it early enough, but it needs to be pretty early. Definitely ask for the source if you can. There's a bunch of platforms you can now buy with open source BMCs, open source system firmware. They will be better and easier to run long term. So if you have purchasing power, go for it. Like, I've never actually reviewed the entire kernel source code, but I believe there is a guy who has. So, you know, that's probably why it's better than most kernels. Right, so to finish off, most people now go, we don't buy hardware anymore, we're in the cloud. A lot of this kind of matters as well. So the cloud is workaround after workaround after workaround as well, just like hardware. You can complain to your cloud provider and they go, your concern is important to us. Please hold. So I think one thing that will work for cloud as well as native hardware is trust but verify. So know what you want to trust when you get VMs. You probably should benchmark your app on all the different machines your cloud provider and maybe other cloud providers have. Different, like if you switch between silicon vendors, you can get a 20% performance bump. And you go, what, really? Just because of that? Try ARM. Seriously, it's a giant bump on some things. It doesn't work for everything, but it's really, really interesting. And we should have tests that'll give us this information. And unfortunately, like eating low sugar muesli, we know we should do it occasionally. We know it's good for us, but it's a lot of effort, not very much fun. Why are we like this? Because we're busy. But elite teams are 4 times less likely to outsource testing than low-performing teams. So if you rely on your cloud provider to do all of the testing and performance testing for your app, you're going to be disappointed, and it probably means you're not elite, and we all want to be elite. Okay, so the other thing is the cloud actually changes daily. We got bitten recently in Reddit with a upgrade to the kernel. We went from the old C groups v1 to C groups v2. All our Go binaries suddenly use 30% more CPU. And it took a little while to notice what was going on. And looking back, they were saying, oh, how could you not have caught this? It's like, oh, we don't benchmark all of the different binaries on all of the different machines and operating system mixes. I suppose we should. We're going to have to. We'll write that down on the giant list of things that we want to do. And I think everyone needs something like a list of QPS per dollar for each of their services. So when that changes, they know maybe we changed the kernel, maybe we changed the operating system, or we went from generation 5 to generation 6 or something like this. You're going to need to find where that has changed and why. Lastly, I think it doesn't matter how detailed your specs are, they're just not good enough, right? I was surprised on a platform a few years ago when I noticed that 0.5% of reboots didn't succeed. And we traced it down to weird firmware bugs, we fixed them. And someone said, what do you mean? You're supposed to have a test that does like 500 warm reboots and then 1,000 cold reboots. And I was like, really excessive? But it would have caught this problem. So if we can share all of these tests rather than every individual company realizing what the tests are each time, it would be pretty cool. The Open Compute project has an effort to share tests and specs for all of these, and there's a cool tool that some friends in Meta maintain called Contest that would be very useful for doing this for VMs and cloud hardware. So if anyone's interested in such a project and would like to do real good testing for cloud and native hardware, come find me afterwards and chat. Thank you very, very much.